Okay, so one other thing I'm going to just show you to start giving you another idea what can happen, and then I'm going to quit, is what's called a velocity selector. And so it really is kind of misnamed because it should be called a speed selector. So this is actually a good example of scientists who are too damn lazy to even differentiate properly between velocity and speed. Okay, so what the velocity selector is basically you have some source back here of electrons. And, oh, Sydney's getting down. Sweet, I can actually draw now. Okay, so you have some source back here of electrons, and it spits, or we'll just say some charged particle, okay? And it spits the particles this way, okay? But they come in like all different speeds. Some are super fast, some are really slow, some are, enormously fast, whatever. But the velocity selector is basically a device that has both a magnetic field, a uniform magnetic field, and a uniform electric field inside. And it puts them at right angles to each other. So here I'm trying to draw a pair of charged plates. So we'll say this one has a positive charge on it, or some positive voltage, this one's negative. Okay, so we can say there's some voltage difference here. But the important thing is there's an electric field, a uniform electric field, pointing from the positive plate to the negative plate. Now, I think you guys know in real life, your electric field is only uniform when you're not close to the edges. You have to get really close to the edges to screw it up. When you get close to the edges, it starts going like this, and then you get like that. Okay, this is something called fringing. And that's mentioned in one of the WebAssign problems. That's why I'm mentioning it. But fringing is just sort of the behavior near the edge of something that should otherwise be uniform. We're going to ignore fringing. Usually people go and mention fringing just to make sure you ignore it. Okay, so we're going to say the electric field goes down. Okay, here. So there's your electric field, which I'm doing in blue. And then I'm going to do the magnetic field in orange, and that is going to go into the page. So these are at right angles. The magnetic field is going into the page. The electric field is going down. Okay, so there's my magnetic field B. Okay, great. So we've got a particle going through. You got your charged particle with charge Q and mass m. I'm just going to write Q and m, so you just remember that. And it's got some velocity coming through horizontally through our velocity selector. Okay, which should be called a speed selector. So it's got speed, whatever. Okay, so its velocity is in the positive x direction. I'm going to use the standard, x, y, and then z is coming out of the page at us. I draw it this way, just say z is coming out at us. Okay, there's a magnetic field B going into the page, or into the screen, whatever you like to call it, and there's an electric field E that goes down. Okay, so what happens to this particle as it enters this region of crossed fields? Well, it gets subject to a force from the electric field, right? And so the force from the electric field, called F sub E, that's just, our usual force from an electric field is just Q times E. We remember this, right? Okay, the force from the magnetic field, which I'm going to call F sub B, since we're using B for the magnetic field, why not use, B here, even though I still don't know why it's B. Okay, and that is Q V cross B. Okay, so your magnetic field goes into the page. That's going to have a force QV cross B. The electric field is going down. It's going to have a force that's just Q multiplied by E. Okay, if we add these together, then the total force on the particle is then just Q times E plus V cross B. This is something called the Lorentz force. After, what's his name? Heinrich Lorentz, I think, a German physicist, I hope, who later actually was really the co-developer of the theory of relativity with Einstein. But this is called the Lorentz force. Okay, this Q times E plus V cross B, and this is sort of the total, what might be called the electromagnetic force acting on the particle. And we'll see how electricity and magnetism are related at some point later, I hope. Okay, so anyway, but the point is, let's go into our velocity selector, and the acceleration then, of course, of this particle, it's in here with this velocity moving through this magnetic field, it gets a force acting on it, which may go up or down depending, right? So actually, you know what? Let's before I go to this, let's make our situation a little more specific here. So I'm going to specify here. I'm going to come up here, and for this situation here. So what I've derived here, this is just sort of the general Lorentz force for any electric field and magnetic field, right? Okay. But what I want to do now is apply this particular situation to it, where you have the magnetic field going in this specific direction, the electric field going in this specific direction. Okay. So here, my electric field is going down. So that is in the negative j hat direction. So that is a negative e j hat is my electric field. Okay. My magnetic field goes into the page. So that is a negative k hat direction. So that is equal to negative b k hat is my magnetic field. Okay. And finally, the velocity I have is v, which is just speed v. It's going in the positive x direction. So I hat. Okay, great. So the force, then, the Lorentz force, I'm going to, excuse me, Mr. Lorentz, let me move you around. There we go. And now, of course, your arrow's not pointing the right way, so we'll fix that. There we go. Okay. So, I want to calculate the force acting on this particle here, right? So, I really shouldn't have put this in the middle, but whatever. Damage done. Okay, so the force is going to equal Q times E, and that is going to equal, so that's going to be negative Q E J hat, okay? And then plus V I hat cross negative V K hat. Okay, so let's I hat cross negative K hat. I actually did this in the last one, but I want to do it again to be sure. IJK, IJ. Okay, so I'm going I cross K. I'm going backwards, so I pick up a negative sign, and then I also have the negative there, so let's cancel out. So the force here is going to be, so carrying this term down from above, the electric field term. And then this is the force from the magnetic field, which is going to be V J hat. All right, fantastic. Now, what does all this mean? No, I'm sorry. VB. Oh, whoops. You know what? I need to. I forgot to distribute my Q properly. Okay, so there we go. Plus Q VB J hat. Okay, so sorry if that was making you antsy. You can relax now. Okay, so let's just simplify this a little bit. And the force on this guy is going to be Q times. Let's just call. Oh, it's going to be Q. Let's just call it negative E plus QV times J hat. Oh, I thought my handwriting would improve when Sydney got down, but it doesn't seem to be the case. All right, and then the acceleration of the particle is going to be equal to, right, Q, well, we just take this force and divide by M, right? So this is just, we take Newton's second law, and we're going to apply it there, and we're going to get Q over M is our acceleration of the particle times, so Q over times, and, no, I'm sorry, this should be a VB. Jeez, I can't do anything right, okay? I apologize. This is negative E plus VB. I left the Q in. First I forgot to distribute it. I can't work now, people. I'm so sorry. Okay. Negative E plus VB. And it's in the J hat direction. But here's the point. We called this thing a velocity selector. There's a reason for that. This is an acceleration. It's going to be in the J direction. And this, what I drew here, this is the particle going right. It's the same coordinate system up here, right? Okay? Because I've still got my electric field going down. I've still got my magnetic field going to the page. I've got my particles going to the right. Here's the deal. What do we need to do in order for this particle to shoot straight through? This acceleration is entirely in the J direction, okay? Which means this acceleration is going to happen up or down. Those are the directions the particle can possibly accelerate. What we need in order for this thing to make it straight through is we need that acceleration to be zero. Because if it accelerates upward, it's going to smack into the top plate, and then it's not going to get out. If it accelerates downward, it's going to smack into the bottom plate, and it's not going to get out. So, what will make the acceleration zero in our velocity selector? So, I'm going to bring it down over here and go acceleration equals zero. u over m negative plus, no, jeez, oh, sorry, negative e plus v, okay, you didn't hear that. Okay, so anyway, so if this is going to equal to 0, be equal to 0, then one of these things, either q needs to be equal to 0, which would mean you're sending an uncharged particle through, which is kind of boring. Okay, you wouldn't do that. J hat is not equal to 0, so that's right out. M can't be 0 because then things become infinity, and then you got a whole crap ton of other problems. So what you need in order to have 0 acceleration, this term in here needs to be 0, term in the parentheses. So that means VB minus E must equal 0, which means the velocity, or sorry, the speed of the particle, sorry, Dr. Osborne, please don't kill me, must be equal to E over B. That is the speed of particle that will make it through this thing. This is why it's called a velocity selector, because what it does is it selects the particles with this speed. Well, it should be called a speed selector, as I said, but whatever. It selects the particles with this speed, which is the electric field strength divided by the magnetic field strength. Anything going faster will have a stronger magnetic force on it, and it'll smack into the top plate, right? Because if it's going faster than E over B, then this term in here will be positive, and so it'll be accelerated upward and smack into the top plate. On the other hand, if V is smaller than this, it'll be accelerated downward, and it'll smack into the bottom plate. This is a velocity selector, and you can sort of imagine you would have like a little dial on your velocity selector that would change the strength of one of these fields or the other, so you could literally decide how fast you want your particles going when they come out, and just turn the little dial to the right setting. And then you only get particles coming out at that speed, which is enormously useful in a lot of things. I don't know. Well, stuff where you need particles, X-rays, and crap. Whatever. I'm tired of talking to you guys. Anyway, there you go. That's so I've done 2 examples now. Sort of, I've done the general particle moving in a circle and a magnetic field, and then this velocity selector thing. And maybe we can talk more if you guys more exciting examples of motion of charged particles. So have a good weekend. Enjoy your 3-day weekend. If you are listening to this before Tuesday, which most of you probably won't because you'll do it Tuesday or Wednesday night, whatever. But enjoy your 3-day weekend. I'll be grading quizzes. No, I'll be grading labs. Anyway,